Hello all, this is section 7 of PLC programming from scratch, and now we're going to start getting into our actual process logic, which is really the heart and soul of a PLC program. Before we get started throwing logical blocks all over ladders, we need to stop, and this is the part where we really think about what we're about to program and visualize the process. What does this machine look like? How does it work? How is it laid out? What did the process engineer have in mind when he created the PNID that we're looking at? And if you don't know what a PNID is, it's a piping and instrument diagram, which is a typical engineering output for any type of piped system. So before we start programming, how do we imagine the process? How do we understand the process? And visualizing the process with something like a visual flow diagram, a cause and effect chart, or even a Visio diagram is a really helpful tool in knowing what your program is going to need to look like, how to divide it up between various ladders. And really, the more you can envision the process from the beginning, the easier your program will be to write. There's a saying that writing clarifies thought, and it's true. When we look at the document on the screen, it's nothing elaborate, it's nothing too highly structured, it's a simple Excel spreadsheet. But it tells us in time exactly what needs to happen and when we're starting up a system. And it's hugely important to have something like this in front of you when you're writing a PLC program. A lot of us can do it off the top of our head, and we get a little cocky about doing that. And more times than not, we spend far more time than we should shaking down and debugging a program before we can load it onto a machine and hand it off to somebody. Another thing we need to consider when we're putting process logic into a program is what are the contingencies? What can go wrong? If we're in the middle of a startup and all of a sudden an alarm condition arises, do we interrupt the startup? Do we sound an alarm and keep going? What needs to happen? What can happen all the way through our process? Murphy's Law says anything that can happen will happen. And in the world of process and automation, that's very true. If it's possible for somebody to throw a shoe into your water tank, it will happen. And when that shoe blocks your discharge valve, what is your PLC going to do about it? You have to think about not only how is the machine designed, how is the machine supposed to run, but what things can happen along the way, and how are we going to handle those exceptions. For the type of programs we're writing in this course, very simple 1 or 2 element systems, a visual flow diagram probably isn't necessary. But in a real world scenario, when you're called to use a PLC, you're more than likely going to be controlling 10 to 20 or more different devices, and on top of that, receiving inputs from just as many. There aren't many people who can keep that many different variables straight in their head. So if you can get as many diagrams, as many flow charts, as many theories of operation written out and on your desk in the beginning, it's going to make your job programming a lot faster, a lot easier, and certainly a lot cleaner. Alright, we are ready to start putting some process logic into a ladder. We are going to start off small, so we are going to control this blower, and we are going to incorporate a concept called HOA control. HOA stands for Hand Off Auto, and this is a frequently used control scheme, particularly for digital devices, or I should say discrete devices. However, it's also used for analog devices although it is a little bit more than just 3 buttons. For now, we're going to look at controlling a digital device in terms of hand, off, and auto. Hand is a technical term for manual, which can be implemented in several different ways, and these are considerations that have to be made up front before programming. When we put this blower into automatic mode, that means the process is going to turn the blower on and turn the blower off automatically. When we turn the blower off, the blower is not going to run under any circumstances. Where we have some flexibility is with the hand or manual control, and there are several different possibilities of how to program hand. For instance, when I push hand and let go, maybe the blower should start running and continue to run until I either turn it off or put it into automatic control. Another possibility is the hand button works like a jog. When I hold the hand button down, the blower runs, but when I let go, it stops running. Then the last consideration is, when the blower's running in automatic mode, can I put it into hand? So with that in mind, we're going to plan for 3 input buttons, one for hand, one for off, and one for auto, and 1 digital output, which is going to our blower, and we're going to write the control logic that allows those 3 buttons to set the status of this blower and ultimately send the signal out to cause the blower to run. So I've got an RS Logix 500 program partially set up. We have a digital I/O file that's empty. We also have a controls file which is empty. And in our I/O configuration, we have inputs set up on slot 1, and we have our outputs set up on slot 2. So the first thing, of course, we need to do is go to our main ladder and make sure our digital I/O and our controls ladders are being called, and they are, so they will both execute on runtime. Next step, as we might recall from the Programming I/O section of this course, we need to bring our I/O into our program, and we need to do it the right way. And the right way is associating digital I/O with bits in a data file. So I'm going to create 4 rungs since we have 3 inputs and 1 output. So we're going to start with our XIC, examine if closed control, and we're going to address that to the first channel of output on module 1. In this case, that's I for input, :1 for slot 1, /0 for channel 0. And we can see that hasn't been described yet. So that's going to be our hand PB for push button input. And we'll go ahead and hit OK without putting a symbol on that, since we don't refer to our inputs and outputs directly. And we're going to associate that input with the bit in our B3 data file, and we're going to do that with this OTE, output energize block, and we're going to address to the first available bit, which is B for binary, 3 for data file 3, :0 for the first element in that data file, /0 for the first bit within that element. And that has a leftover description from the last example we used. So we're going to go ahead and reallocate this bit. Since it's not being used anywhere else in the program, that's not going to hurt anything. And we're going to call it hand PB, since it's associated with our hand push button. Now we're going to follow the same example and set up our off and auto push buttons the same way. So our off push button will be coming into the same input module I:1, only this time it'll be on channel 1, and we'll go ahead and call that off PB input. Again, no symbol because we won't be referring to that outside of our program. And we'll go ahead and take the next available bit, which we're also going to have to reappropriate, and we're going to call that our off push button. And in the future, this is what we'll be referring to when we want to see the state of that button. And our last push button is going to be our auto push button. That's going to be on input module on slot 1, channel 2, and that's going to be auto PB input. And we will go ahead and tie that to the next available bit, which hasn't been described yet, and we'll of course call that auto PB. We'll go ahead and give it a symbol just in case we ever want to refer to it outside of the program. And that does it for our inputs. We only have 3 push button inputs on this program, and we have 1 output, and that output is our blower. So we will give it a control bit first of all in the same data table. That'll be B303, and we'll call that quite simply blower. And we'll have to use an output energize to associate that to the actual output to the blower. Now our input module is on slot 1, and we have our output module set up on slot 2. And that has to do with where it's connected physically to the PLC's backplane. So we'll go ahead and define this as O:2/0, which is the first channel on module 2, and we'll define that as our blower output with no symbol. And now our I/O for this program is completely set up. We have our 3 push button inputs, and we have our single blower output. And there's nothing else for us to do in our digital I/O ladder. So everything else we are going to do with this falls under controls. So we'll go ahead and go into our controls ladder, and we'll be referring to the bits we set up in here. So the first thing we'll want to do is look at B300, B301, and B302, because those are our inputs which will be setting the state for this blower. So in our controls ladder, I'm going to go ahead and add a few rungs. I might have to delete 1 or 2 when we're done. The first thing I want to do is use an examine if closed, and I want to look at our first push button, which we brought in on an input channel, but then we directly associate it with B3:00, and there's our hand push button. And we want to be able to set a status that will be used to control the blower and how it operates. So we know we have 3 different states that we want to have for our blower. We want it to either be in hand mode, off mode, or auto mode. So we're going to use an integer value to store the state. We can't obviously use a bit because a bit only has 2 possibilities, 0 and 1. The next alternative for us is an integer, and that can store 3 or plenty more values. So let's go ahead and use a move command. And we're going to call hand state 1, and we need to set an integer memory location. We need to set up a register to hold this status. So back to our data files, we know our integer file is N7. So let's go ahead and set N7, and we'll take the first available integer, which is N70. We can see that's been defined in a previous example, but since it's not being used anymore, we can go ahead and reallocate this integer. And we're going to call it blower state. And we're going to go ahead and define what our actual modes are. So we'll call a value of 0 the off mode. We'll set 1 equal to hand mode. And we'll set 2 equal to automatic control. And just in case we do want to know what mode our blower is in from an external application or HMI, we'll go ahead and define this symbol of blower state. So now, if somebody presses the hand push button, we're going to move the value of 1 into the integer location N7:0. Now I'm going to put one more control onto this rung. If you remember back in the section on programming fundamentals when we were going over the different instructions, we mentioned something called a one-shot. And one of the reasons we use that is because a PLC scans the program so many times a second that when a person's finger is on a push button, the PLC can run 10, 20, or 30 scans during that time. And when we want a push button to trigger one single instantaneous action, we need to program our control logic so that a single button push doesn't cause the same action to happen 20 or 30 times. And the one shot is the instruction that allows us to do that. So let's go under bits, and we're going to go ahead and put a one shot. And of course we have to give that a location. And I'll just go ahead and name it one shot so we know what it is if we're looking into the data table. So now when somebody pushes the hand push button, even if they hold that button down for an hour, we're only going to be moving the 1 into the location N70 one time. And we can go ahead and follow that same pattern with B3:0/1, which is our off push button. We already know we're going to want to go ahead and use a one shot, which we'll name one shot again just so we know it's another one. And then we're going to use the move command one more time. And this time we're going to move a 0 into the N70 location. And 0, if we remember back in this description, we recall is the value representing the off state. And let's go ahead and wrap our inputs up. We're going to go back to B3:0/2, which is our auto push button. We're going to give it another one shot, and remember all of our one shots have to have their own individual addresses. So right now for one shots we're using B304, B305, and B306. We cannot use those 3 bits for anything else in our program. And let's pull our move command down one more time. And this time we're going to set a value of 2 to our integer N70, which we're going to be using to monitor the blower state. And the last thing we want to do, we're going to want to actually energize our blower. So let's go ahead and put the output energize on rung 3. And I don't remember what that address was. That's B303. And let's look back to our digital I/O to see what the bit was for the blower. And here it is. We set up B303 to control our blower. So here is where we're going to go ahead and energize B3:0/3. And now we need the conditions under which the blower is going to come on. Well, the first thing we know is when the blower is in hand control, which is defined here as state 1, we want the blower to be running. So we're going to come into the compare menu and we're going to take the equals instruction and we're going to look at N7 0 and we're going to see if it equals 1. And if N7 0 equals 1, then our blower is in hand mode and it should be running. Then we also have an automatic mode. So we need to give it another possibility. We're going to bring down this branch and stretch it around our equals block. Now this equals block is the only condition we have for the blower to run if it's in hand mode. But if it's in automatic mode, then we're going to rely on another piece of logic somewhere else in the program to activate it. So let's come back to our compare tab and let's bring down another equals command. We're still looking at our status integer for the blower, that's N7 0. This time we want to know if it's in auto mode. And we're going to need another bit to energize elsewhere in the program when the blower is needed. So we're going to take the next bit address and we're going to call this blower auto energize bit. So when we have a greater program and that program is controlling a full process, it's going to determine when the blower needs to come on, and it's going to do that by energizing this bit, B307. And if our blower is in automatic mode, meaning that N7 0 is equal to 2, then the blower will run. But even if we energize this bit, if the blower happens to be off, in other words, N7 0 is equal to 0, then this B307 bit will not make the blower come on all by itself. So right now we have a pretty good HOA program for our blower. If there's one other thing we might want to consider, that is, when we push these buttons, do we want them to work absolutely? In other words, if we're in auto mode, do we want to be able to go straight into hand? And if we're off, do we want to be able to go straight into auto? Or if a greater process is running, do we want the ability to take the blower out of auto? So aside from what we have here on rung 0, 1, and 2, we might actually decide we want to put some more commands in. So let's say we want to be able to put the blower into hand, but only if we were previously in off mode. And if we were in auto, we don't want to be able to go into hand. So right now, if we push the hand push button, it's going to go into hand mode regardless. So let's go ahead and add one more condition to hand, and let's say that N7 0 cannot be equal to 2. So now when we push the hand push button, the first thing that's going to happen is the program is going to look to see if the blower is in the auto state. If it is, then this rung is not going to execute its output, and it'll stay in the auto state. But if we happen to be in off, or if we happen to be in hand, this one shot's going to go ahead and fire for one scan, and we'll go ahead and move the value 1 into N70, even though it might already be there, in which case this won't have any effect on our program, but it did execute regardless. So now we can clean up these extra rungs that we didn't need. Let's go ahead and verify our project, and we didn't get any errors appearing down here, so we have a good viable project. And if we needed a PLC program to control nothing but 3 push buttons, hand, off, and auto, and 1 blower, then our job is done. Okay, for our next example, we're going to write a PLC program to control the machine in front of us. We have a pump that fills a tank. Within that tank, we have 4 float switches at various levels. You'll recognize here we have our high level, our high level, our low level, and our low level. And we also have a discharge valve naturally located at the bottom of the tank, so it'll be gravity fed. And we're going to write the program that will fill and drain this tank. So once again, I've set up a largely clean PLC program. I've got our main ladder calling our digital I/O and our controls, which are the only ladders we'll be using. On our I/O configuration, I still have 8 inputs on slot 1, and I have 8 outputs on slot 2. All I/O are digital. And we're going to jump right into bringing our I/O in. So, going back to our graphic, we have 1, 2, 3, 4 inputs, and we have 1, 2 outputs. Those are our pump and our valve. Let's go ahead and start laying these out, and I'm going to work through this a little bit more quickly than I have in past examples, because I know you've been keeping up. I know you understand this by now, and I don't want to kill you with redundancy, but I certainly do want you to understand and retain these things. So let's go ahead and address our first input. That's on slot 1, channel 0. And we're going to go ahead and call that our low switch. Then we're going to associate that with a bit in our data table. We'll take our first one, B300, and we'll define that as our LL switch. Now, just to program a little faster, I'm going to go ahead and copy rung 0 and paste it 3 more times. And I'm going to copy and paste my way through some of this. So I just copied the description out of I:1/0. And I'm going to change the second rung to 1, which is our next channel. And that's just going to be L switch input because that's the low, not the low. The next one I'll set is 2, and this one's actually going to be H for high. And the last one I'm going to set for 3, and we're going to call that HH, which is high. And just like we did that on the left, I'm going to come over here and cheat the same way on the right. So we have an L switch, then we have an H switch. Again, that's our high switch. And last but certainly not least is going to be our high switch. And you'll remember that LL and HH are for alarm conditions. So I'm programming the alarm level switches in here, the LL and the HH. But I'm not actually going to program the alarms just yet. We are going to hold off until the next section on alarms and notifications, and we're going to come back to this program and we're going to put those in at that time. But we've gone ahead and set up the I/O now, and now we've got 2 more. That's going to be our digital outputs. So the first thing we need to do is establish control bits for them. We have one that's going to be our pump. And we have one that's going to be our valve. And we need to tie those to the output. So we'll say that our valve is on output 2 channel 0. And we'll put our pump on channel 1. So that is it for our I/O. We've got that all mapped out. Now we're ready to jump into the exciting part. That's the controls, and figure out how we want to make all of this stuff work. The first thing we know we want to look at is our low and high switches. Remember, those are process control. Low, low, and high, high, those are for alarms. Right now we're just programming process control, so we can forego worrying about the LL and HH until we get to the next section. So we're going to be pulling B301 and B302 into our controls. So let's create a few rungs here. We're going to go ahead and use XICs, examine if closed blocks. And we're going to go ahead and look at our low and high switches. Then we also know we're going to want a couple of rungs that are going to energize our pump and our valve. So let's go back and look. Those are on B304 and B305. So we're going to go ahead and put output energizes on B304 and one for B305. So we've got our inputs, we've got our outputs, and now all we have to do is put some logic in that makes these things work. So when we think about our tank, we're going to really be running two modes. We're going to be running a fill, and we're going to be running a drain. Now the way I'm envisioning this working right now is when the pump is running, the valve is closed, and that's going to fill our tank up to the high level, and then the pump is going to shut off and the valve is going to open. That's going to drain our tank down to the low level. When we get to the low level, we're going to close our discharge valve again and start our fill pump. So this maybe isn't a very practical operation, but we want this tank just to fill and drain and fill and drain and cycle back and forth, and that's what we're going to program it to do right now. We're going to look at the low switch, and when that's going to tell us when the level is low. That means it's going to trigger the fill mode. So when we're setting modes, we can use an integer if there are more than two modes, or we can use a bit if there's only two modes. So in this case, we only have two modes, and we've already seen an example of using an integer to control status with our blower example. So this time I'm going to use a bit to control the mode. So our low switch is going to energize a bit, and that is going to set our fill mode. And when that bit is de-energized, we're going to call that our drain mode. The thing is, if you understand anything about levels of fluids or liquids inside of a tank, especially when you're pumping into that tank or draining with a valve, you know it's not always a smooth level on the top. The pump especially tends to create some waves. And when you're working with level switches, again, you have to consider reality when you're writing a PLC program. When the level is right next to that switch is going to be rocking back and forth, open and closed, open and closed. If we're triggering our pump based directly on that switch, then our pump is going to be starting and stopping back and forth, and it's not going to take too long before our pump burns up. The valve will be doing the same thing, clicking and chattering back and forth, and its actuator is going to burn up. So we need to put some smart code into this program that's not going to allow the pump to rock back and forth, is not going to allow the valve to open and close repeatedly. And the way we're going to do that is we're going to use delay timers to establish these modes. So I'm going to go to timer counter, and I'm going to use our timer on delay, and I'm going to set a timer T40, and that's going to be our fill mode delay timer. And we'll go ahead and leave that as a seconds timer. We don't need milliseconds or hundredths of a second for this kind of operation. And let's call it a 10-second delay on that timer. What that means is when this level switch is closed, and that's going to happen when the water level drops down below the low level switch, then this timer is going to energize and start timing, and we're going to get a down bit out of that timer. So let's go ahead and add a couple of rungs in here, because we still haven't set a mode for anything. All we've really done so far is energized a timer. So we want to analyze that down bit for T40, and that's our fill mode delay timer. If you remember back from programming fundamentals, the way that a timer works is when it times all the way down, this down bit energizes, and it'll stay energized until this rung is deactivated by rendering the conditions to the left as false, or until a reset command is activated against this timer, rocking the accumulator back to 0. So right now we're not going to worry about resetting that circuit. We're going to worry about when this fill mode delay timer times out, then we want to go ahead and set a bit, and this bit is going to be fill mode equals 1, drain mode equals 0. So this is our control bit, and we'll go ahead and give it a simple symbol as well, fill mode. Okay, so now let's think through this. When the level in our tank gets down to the low switch, it's going to rock back and forth a little bit, and this timer's going to start and then stop and reset itself and start again. But that water level is going to keep going down, and pretty soon it's going to get far enough below this switch that it's going to close and stay closed. And when that happens, then this timer is really going to be able to make some progress and start counting up. And once it times all the way up to 10 seconds without the water level creeping back up, then this down bit's going to energize, and we're going to start fill mode. Now we already know once we start fill mode, this system's going to start filling back up, and the level's going to come up above the low switch pretty quickly. Once it does, the way this program's written right now, the timer will de-energize, the down bit will be lost, and this mode is going to change right back to drain mode. And that means our water level is going to start going down again. And that's not good process control. If you remember, we want it to go down to the low level, then we want it to start filling and stay filling all the way up to the high level. So what we need is a latch, something that once this fill mode bit is triggered, it's going to lock it in, and even when this bit for T40 is lost, we want something to hold this until we get up to the high level. So we're going to put a branch around this condition here, and we're going to use this bit as its own hold-in. So we're going to put an XIC, and we're going to address it to B306. So we're referring to the bit that's energized on the same rung. And let's step by step through just this rung so far. What's happening is when this timer times out, then this down bit is going to energize, and it's going to energize this bit right here. The next time this scans, now this is going to be energized, so we have a path through here on the top branch of this rung. We also have a path on the bottom branch. So fill mode is going to stay energized. The level in our tank is going to start coming up, and eventually it's going to go above the level switch, which means this timer will reset and its down bit will open. But since this was already energized, this will still be true, and we'll still be able to come in around this down bit, and we'll still have a path to keep this fill mode energized, and it'll stay energized and keep filling the tank. Now we need a way to terminate fill mode. So let's look to our high switch once again, and the same problem we had when our level was at our low switch, we're going to have at our high switch. That means the water level is going to rock back and forth, and this switch is going to open, close, and we solved that above with a timer, and I don't see any reason why a timer won't work here as well. So this is going to be our drain mode delay timer. We're going to go ahead and set that as a 1-second timer, and we're going to give it 10 seconds as well. And now we're going to use the down bit of this timer as an interrupt for the hold-in circuit on this rung. So we're going to use the XIO command, and we're going to address that to the timer 41's down bit, T4:1/DN. So let's step by step through this again. We already know that this timer is going to trigger this bit, which is going to energize this bit, which is going to make this true, and that gave us a path through this branch to sustain this even once we lose that. Now, as of yet, our drain mode delay timer, that's not going to start timing until our high switch is met. So this down bit is going to be open. It's going to be de-energized. And that's good because we're looking at that bit and saying we want it to be de-energized. And as long as it is de-energized, this instruction is going to be true, and our fill mode is going to be locked in, and it's going to keep going up, up, up until our high switch is met for 10 straight seconds. Then we're going to energize our down bit, making this condition false. We already know this is still going to be false. This will be false. That means our fill mode is going to be lost, de-energized into drain mode. And it's going to stay in drain mode until we re-energize with our low switch and the fill mode delay timer. So right now we've got the code necessary to control this fill mode bit. Now all we have to do is connect the fill mode bit to our pump and to our valve. So when do we want our pump to come on? We want our pump to come on during fill mode, which means when B306 is true. So let's use an XIC instruction and tie it to B306. So now our pump will come on anytime we're in fill mode. As for our valve, we want that to work in drain mode, which means this fill mode bit needs to be false. That's as easy as an XIO command, which is the exact opposite of what we used on rung 3. We're going to address it to the very same bit, and we're done. So now, when our fill mode bit equals 1, which means it's closed, that's why we're using an XIC command, our pump comes on. And when our fill mode bit equals 0, that means it's in drain mode, then our valve comes on. And by on, we mean that's going to actuate into the open position. And we want the pump and the valve to work opposite each other. And that's perfect because we're using the same bit to control them both in opposite polarity, which means they'll never be actuated or energized at the same time, and you'll never have both of them off at the same time. One will always be going, the other one will always be at rest. So that program should make sense to you at this point. If it doesn't, please watch this lecture again, look at the logic, work through it in your head without my voice, just pause the video, work through the logic. Once all this makes sense to you, start up the next lecture, and we're going to transition this program from digital controls to analog controls. So this was a bit of a more complicated lecture, I understand that. The next one is going to be somewhat of a break because we're not really going to be originating a whole program from scratch. We're going to be modifying an existing program. And in the life of a programmer, that's something you have to do from time to time. It'll be determined in the field that a means of control isn't satisfactory for the process and they want to retrofit an existing design, which means you're digging into a year-old program or a 3-year-old program that you maybe didn't even write, and you're changing digital controls for analogs, you're adding redundant controls, you're changing the way things work, and I pay a lot of my bills retrofitting old programs that I didn't write. Well, assuming you've got this program figured out and you understand how it works line for line, instruction for instruction, we're going to go ahead and retrofit this program. We're going to take out the digital controls and we're going to replace them with analog controls. So when we look at our tank, it had 4 float switches in it. Now imagine we're going to put a radar, an ultrasonic level sensor, right on the top of this tank, and we're going to take these 4 level switches out. So back into our program, we know we're going to be using a little bit of analog, so let's go into our I/O configuration, and we're going to have to add an analog channel. So let's go ahead and put an analog 4-channel input here, and we'll configure that with our famous 4-to-20, and we'll go ahead and use scaled for PID, and we won't worry about reconfiguring the other 3 channels because we're not going to be using them anyway. So let's keep in mind that our analog input is on slot 3. That's going to help when we address it. And for now, let's get rid of all of this digital I/O because we're not using it now. So what's left in our digital I/O is just our output to our valve and our output to our pump. And in our controls, we have this low switch, which we're going to get rid of, and this high switch, which we're going to get rid of. So that is all we needed to do to take the digital out. Now we need to put the analog in. So we already have a ladder for digital I/O, but since that ladder is kind of empty, we're going to go ahead and rename that and make it all kinds of I/O. So now it's just going to be plain old I/O, and we can go ahead and put some analog into it. So we're going to hunt down our scale with parameters instruction all the way at the end under advanced math. And we remember our input is on slot 3, and we're looking at channel 0. And it looks like that is already described as something, so we're going to change it, and it's going to be level sensor input. So now we have to have a minimum and maximum input range for that input. And remember, we scaled that for PID, which means the minimum is 0 and the maximum is 16,383. And then we need to scale an output minimum and maximum. And level sensors sometimes work on distance, and sometimes they can be calibrated. And most of the time, unless you're going really cheap on a project, you'll use a level sensor that can be calibrated. So we're going to just go ahead and treat this like 0 to 100%, which is a full tank. And we're going to output this even though we'll be losing a lot of resolution. When we're controlling a tank level, we really don't need the precision. We need to know within 2 to 5% what level that tank is. We don't need to know that it's 64.2783%. It's not a nuclear power plant. It's not a silicone wafer fab. This is just controlling the level in a tank in a trailer park in Indiana. So we're going to go ahead and store this as an integer value, which we'll call quite simply level. And that's all we're going to do to bring this analog signal in. We're not going to worry about any conditional scaling or low signal values or high values, because we're not going to be doing any kind of math with this level. We're just going to be displaying it and using it for basic process control. So let's go into our controls. And we don't have level switches to trigger our 2 delay timers which initiate fill mode and drain mode anymore. So now we're going to have to compare an analog value using a comparator. So let's go into our compare tab, and our fill mode is triggered by a low level. So we're going to look for our level to be less than a certain value, and let's go ahead and call it 20%. So if our tank level is less than 20%, and you'll remember from I/O that we scaled that from 0 to 100, if we're less than 20%, we're going to do exactly what we did in the last lecture. The rest of the program hasn't changed. We're going to start that timer, and that timer is eventually going to trigger fill mode. And we're going to do the exact same thing. We're going to fill in the missing blank on the left side of our rung to initiate drain mode. And if we used a less than command to trigger fill mode, you can bet your bottom dollar we'll use a greater than command to initiate drain. So we're still looking at our level, which is N70. And this time, instead of 20%, we'll look for the level to be greater than 80%. And if it's greater than 80% and it sustains a level greater than 80% for 10 consecutive straight seconds uninterrupted, then we'll go ahead and interrupt the hold in for fill mode, thus initiating our drain and closing our valve and starting our pump. And transitioning from digital controls to analog controls is just that simple, especially when you've properly segregated your I/O. It makes everything a whole lot easier. So take a long look at this program, look back through the lecture if you need to, make sure you understand how the analog signal is coming into our PLC, how we're processing it, how we're converting it to a 0 to 100 range, how we're evaluating that level against set points to determine when to start our fill and when to start our drain mode. Once all of this makes sense, go ahead and start up the next lecture, and we're going to be looking at a PID control loop, not exhaustively, but at least a little more closely, so stick around. Okay folks, let's workshop. We are going to set up a program to control a heater based on temperature. And we're going to take this through several iterations, beginning with digital control. Then we're going to upgrade our system to analog control and incorporate a PID control loop. And I'm going to give you a very basic, simple, down and dirty tuning technique, which will usually allow you to set up a largely stable PID control in a system. However, for faster operations and more sensitive operations, you'll want a more robust tuning methodology. So let's get started setting this program up to control a heater. The first thing we're going to do is jump in and configure some I/O. As you see, we've got our MicroLogix PLC on slot 0, and we want to go ahead and add some digital input and some digital output. So we're going to take a digital 8-channel input on slot 1, and we're going to go ahead and give ourselves 8 digital outputs on slot 2. Neither of those requires any configuration whatsoever, so we're done. Now, we know best practice is to set up 3 or 4 or 5 or 10 ladders to hold all of our code and keep everything separate. In this example, I want everything kind of on the same ladder because A, it is a very simple program that we're writing, and B, just so we can look back and forth and see what's going on and make the changes without having to jump from ladder to ladder, I'm going to put it all in ladder 2. So bear in mind that's not a best practice that you want to observe every time you write a program. I'm giving you a bit of a bad example here, but for the sake of learning this a little bit more easily, I'm going to go ahead and put it all in the same ladder. I'm going to begin by creating us a handful of rungs to start lobbing code on. And the first thing we're going to do is set up an XIC and start addressing and bringing in some input. So we're going to not worry so much about high and low. We're not going to look at alarm conditions right now. We're just going to focus on process control. I want to keep it very focused so you get the idea of the controls and the PID, and this isn't so much a lesson focused on best practice. So normally, especially in something like a heater circuit, you're going to have a high, at very least a high alarm. So we're not going to do that this time. We will look at better, more robust programming later on, especially when we go through our full demo program step by step. But in this case, let's just focus on controls. So we're going to address our first input as input module 1, channel 0, and we're going to set that up as our low temp switch input. And of course, we wouldn't put a symbol on that because it's not something that we would ever look at from outside of the PLC program. We don't look at inputs and outputs directly, but rather the bits and floats and integers we assign them to. And we're going to associate that input with a bit. We're going to take our first bit, our classic B3:0/0, and we're going to call that our low temp switch. And here we would generally put a symbol, but for the sake of keeping on track with this lesson and not worrying about a lot of distraction, I'm just going to leave everything with descriptions only. So we've got a low temp switch, but for good two-sided process control, we're going to go ahead and put a high switch as well. Mind you, low and high are process control set points. unlike low, low, and high, high, which are usually alarm limits. So we're going to take our next input channel. That's going to be input 1, 1, and that's going to be our high switch input. And of course, we're going to associate that with another bit and call it high switch. And that is all the input that we're going to use for the time being. And we want to use one output, and that's going to be our heater. And this heater is going to be a simple digital heater. It's going to turn on and it's going to turn off. There's not going to be an analog signal telling us how hot or how many BTUs or how much gas is going to this heater. So our output we set up on slot 2. So this is going to be O:2/0, and we're going to call that heater output. And of course we're going to need a bit in the driver's seat to control that heater. So we're going to take our next bit and call that simply heater. Now we need a conversion. You remember a PLC program is inputs, conversions, and outputs. We've got our inputs, we've got our outputs, so now we need a conversion. So we already know the goal of this next rung, and that's going to be to energize our heater bit. So let's just start with our output to B3:0/2, which is the bit we set up on our previous rung to control the heater. And now we need a condition for when this heater is going to come on. We have a low temp switch and a high temp switch, and obviously a heater is going to raise the temperature. So that tells me that we're going to be switching from the low temp to cause the heater to come on. So let's evaluate with an XIC, examine if closed block, and look right at this low temp switch bit that we set up to keep up with the input from our low temp switch, and that's B3:00. So now, whenever our low temp switch is closed, our heater is going to come on. But what happens next is our temperature is going to start rising, and our low temp switch is going to open, and then our heater will shut off immediately. And that is not desirable, because what happens when that heater shuts off is we stop heating, and we're never going to get back up to our high switch. And what we don't want to do is work this heater to death and burn up the relay, turning it on, off, off on a very short interval. So we're going to create a hold-in circuit by putting a branch around the low temp switch condition on rung 3 that energizes the heater, and we're going to use the heater as its own hold-in by putting an examine if closed on this branch and tying it directly back to the heater bit B3:02. So now when this program executes, it's going to pull the first input, pull the second input, it's going to come to rung 2, it's going to look for the heater bit to be energized. It's not going to be, so this output won't be energized. It'll come down to rung 3, and depending on the state of our temperature switch, the heater will either come on or it won't. But since the heater isn't energized yet, this sub-branch with this XIC on it can't possibly be true. So the only way the heater will come on is if the low temp switch is closed. So let's assume that the low temp switch is closed, and then the heater will energize, and our hold-in will become latched, and it'll stay energized forever because we have no way of turning off this hold-in. Well, we know we want to turn it off eventually, and we want to turn it off based on our high switch. So we want to turn the heater on when we get to the low temp switch, So once the heat rises enough that the high temperature switch closes, we want to disable our heater. So we're going to use an XIO, examine if opened condition, and we're going to assign that to our high switch bit, which is B301. So now the low temp switch will turn our heater on. Once the heater's on, it will hold itself in with this sub branch, and it will remain on until the high switch is closed. So as long as the high switch is open, this XIO block is going to evaluate as true. Once the high switch is energized, our heater will turn off, and we assume our temperature will start to fall, and this cycle will continue and repeat. So this is our full program. Right now we have a heater that's an on or off heater. There's no analog control. We have two inputs, a high temp switch and a low temp switch. And we have the necessary control logic, which is rung 3. That's our conversion from input to output. And that's going to make the heater do what we want it to do. Now we're going to assume that maintaining temperature within a certain range isn't good enough for a particular process. Now we want to maintain temperature at a specific set point rather than, let's say, between 80 and 90 degrees. We want to be able to set that temperature at 82 degrees and the temperature stay there all the time. So now we're going to get rid of our digital controls and we're going to replace them with analog, and we're going to use a PID control. So the first thing we're going to need is I/O. We have digital input and digital output, but we can't use ones and zeros anymore. Now we have to use some bigger numbers. So we're going to go ahead and add an IF4 module, which is a 4-channel analog input module to slot 3. And then we'll go ahead and put a 4-channel analog output module on slot 4. And we'll very quickly configure one channel of each of these to 4 to 20 milliamp scaled for PID. There we go. And now we're ready to program. So at this point, everything we have in our program is digital, and we're going to go ahead and delete it all and not use any of that anymore. And now we're going to look at this as a completely analog process. So the first thing we need to do is bring in our analog signal from our temperature sensor. We're going to do that with the scale with parameters block. And we know we're looking at input from module 3, channel 0, and we're going to go ahead and call that temp sensor input. Our input minimum and maximum, we remember we scaled this for PID, which means our low input value is going to be 0, and our input max is going to be 16,383. And now we need a minimum and maximum for our output. That is going to depend entirely upon our temp sensor. So let's say we have a temp sensor that reads from 32 degrees Fahrenheit to 212 degrees Fahrenheit, freezing and boiling point of water. So we have 32 as a scaled minimum. We have 212 as a scaled maximum. And we're going to go ahead and save that as an integer. And I know what you're thinking, wait a minute, Paul, you're losing all of your resolution if you do that. That's correct. We are losing a ton of resolution, and we're doing that strictly for demo purposes right now, just because we're worried only about a PID setup. So instead of maximizing resolution like we would under normal best practices, in this case we just want to keep it short and simple and go straight to PID with an integer in a simple value range. So we're going to call this temperature. And then of course we're going to need an output. And normally we would scale an output the same way we scale an input using SCP. But this time, since we scaled our output for PID, we're going to be able to go straight from our PID to our output, to our temp controller. So instead of putting the output first, let's go ahead and put in our PID control. So let's look through our menu, and we're going to go under File Miscellaneous, and here is our PID block. We're going to go ahead and drop that in on rung 1, and we need to give this a PID file. Now right now a PID file doesn't exist in our data file, so let's right click on Data Files, select New, and take Type PID, and we'll go ahead and give it a name of temp. So now we have a new data file, PD9, and that's our temp PID file. So our PID file on our control will be PD9, and we need a process variable. Now we remember PID control from our Programming Fundamentals section. Process variable is the variable that the PID control looks at when it's trying to set the output. So the process variable is what it wants to read on the set point. It's going to adjust a control variable to make the process variable attain and maintain the set point that we put in. So we're going to give it a process variable from our input, and that's going to be N7:0. And we need a control variable, something going out, so we're going to arbitrarily assign it to the next available integer, and the system's giving us N7:1, and that's going to be our PID output. So now we've got this very intimidating PID setup window that opens. We're going to get into KC, TI, and TD a little bit later, but for right now we're just going to set the input and output and our time mode. We can use a time mode based on STI, which is selectable timed interrupt, but in this case we don't want to have to set up a function file, so let's just go ahead and put that on timed mode. And let's start looking at our scaled set points. We're going to give this a set point somewhere within our temperature range of 32 to 212 degrees. And if you're like me, you appreciate a room that's about 72 degrees. So we're going to go ahead and assume it's a wintry cold day. We're controlling a heater to our house, and we want it to maintain 72 degrees. Now our set point max and our set point min have to do with that process variable that we're bringing in from our temperature sensor. So we know we're bringing in N70 as our process variable, and we know that we scaled that on rung 0 from 32 to 212. So our max is going to be 212, and our min is going to be 32. Now when we look below, we see process variable here. This isn't something we set up. This, if you notice, is a little bit gray. It's almost indistinguishable. But this is just for display purposes if we're opening this window while the program's running, so that we can see what the process variable is. So when you look and see a 0, that's not something that we set or change. That's something that's automatically updated on runtime. So the next thing we need to do is we need to come down here and worry about our output setup. We have our control output, and this is all in percentages. So in output, the first thing that we see is control output, CV percentage. This is something that we can fill in, but that is only if our PID control mode over here is in manual. We are not going to do manual because that kind of takes all the fun out of PID control. We are just going to run this in auto, which means we can leave that at 0. The system's going to automatically set that according to our input, and that's what we want it to do. That's auto control. Okay, so the next thing we have to fill out is our output max and our output min. And if you look, these aren't max and min values. These are min and max percentages. So we can put 100% for our maximum and 0% for our minimum. And that doesn't give us any dead band on the top or on the bottom. And that's something that you'll probably want to do in a real-world application. But to keep it simple and to demonstrate the idea of PID setup, we're just going to go ahead and put it at 0 to 100%, although 5 to 95% might be preferable. And that's our initial setup. So the next thing that we have to do is move this control variable in7:1 to our output. And to do that, we're going to use a very simple move block on the next line, and we're going to move in7:1's variable to our output location. We're on output module 4, channel 0, and we'll go ahead and call that our temp controller. And that is it. That is our entire program now, which if you look at, it's quite a bit simpler and a little less logic than our digital control, and it's a lot more robust. The only problem is the PID loop has to be tuned, sometimes need adjusted, and that can be a bit of a tricky process. So I'm going to go ahead and explain to you one simple technique which will probably work for you most of the time. Otherwise, you will have to take more drastic steps to get your loop tuned. So when this program is loaded onto a system, and this is not a process that can be done any time before you're actually up and running on the live system. So caution is recommended, and you want to be aware that if you change a variable too drastically, you can cause a process to become unstable and you could potentially damage equipment or kill somebody. Take this process, do it slowly, and if you have never done it before, please don't experiment on anything that can cause a hydrogen explosion or release toxic gas or anything to that effect. Assuming that we're up, we're running, we're connected to our heater, and we're receiving input from our temp sensor, we want to let the system run for a few minutes until we see what the process is doing. We want it to be stable. Now when I say stable, it might not be steady, but we do want it to be doing the same thing continuously. If it's looping out of control, if it's shooting way too high and then going way too low, that's okay at this point, but whatever it's doing, we want it to be doing on a regular predictable interval if possible. So we're going to start making adjustments to K, C, and TI. Right now, in this process, we're not going to worry about TD. When we're looking for a good definition of what these things are, because again, if you're not experienced with PID control loops, these look pretty intimidating. The good news is the help menu in this program does have phenomenal explanation for most of the controls. So we're going to go ahead and click the help and look right at what's built into this program. KC is our controller gain, and it tells us right here this is the proportional gain. Generally set this gain to 1/2 the value needed to cause the output to oscillate when the reset and rate terms are set to 0. Then we have our reset TI. That, it says, is our integral gain. Now remember, the PID has 3 different formulas that are running potentially. And those are proportional control, integral control, and derivative control. The KC is the gain on the proportional. The TI is the gain on the integral. And then we have a term for the derivative. So back to the TI, generally set the reset time equal to the natural period measured in the gain calibration above. So that involves a little timing when you're making the KC adjustment. And then for our rate term, our TD, it says to set that value at 1/8 of the integral time above. So that is a process to tune a loop, but it is not the process that we're going to look at right now. We're going to try something just a little simpler. We are not going to worry about setting the TD because in a lot of cases, I would say most cases, unless you have a very fast process or a very sensitive process, you can get away with tuning this way. Once your system's running and you're online with your PLC, you're going to adjust your KC up very slowly until your system starts to oscillate. And if you don't know what oscillate means, that means your temperature is going to go a little bit above the set point, then it's going to fall back down a little bit below the set point, maybe, or it'll just go a little bit above and fall back to the set point, depending on how powerful your heater is. But it's going to be going up and down eventually. And once it starts going up and down on a steady basis, we're going to cut that value down. I know it said to half of the oscillation, but we're going to cut it down to 2/3 of whatever set point we had in there to make it oscillate. Then we're going to do the exact same thing with our TI. We're going to start raising that with the KC set point already established and loaded. We're going to raise the TI until we get to a point of oscillation. Then we're going to cut that down to 2/3. And chances are we can call it quits right there, and we'll have a sufficiently stable process running. If that fails, then you're going to want to go back into the help menu, do the slightly more complicated prescribed method, and if that fails, there are several other methods floating around out there and even tuning software to tune that loop for you. So again, this is not amateur stuff. This is not something that you're going to learn in 5 minutes. This is something you're going to have some real world experience practicing with to get good and to get comfortable with PID controls. So now that we've discussed tuning a little bit, let's go back and consider one more layer of complexity, and we're going to look at our input scaling. What we have is a scale range of 32 to 212, and we've established that right here inside of our PID control. And what we want to avoid is sending any input into that PID on the process variable that is outside of this range, because we do not want unpredictable behavior. So we're going to put some conditional scaling on this input. We'll start by adding a branch and putting our scale with parameters instruction inside of that. And we're going to go ahead and extend that branch one level down so that we have 2 extra lines to put some conditions on. And we're going to look for a low signal with a less than command and a greater than to look for a high signal. So in both cases, we're going to be looking at our input I30, and for our low end, we're going to be looking at anything less than 0, and for our high end, we're going to be looking for anything greater than 16383. And depending if we have either of those conditions, we're going to want to execute a move, and we're going to put the high and the low levels into N70. So our low level is 32, and our high level, of course, is 212. So what's happening here is the first thing that happens is we're going to scale our input and we're going to store that value in N70. But before we leave rung 0, we're going to run these two sub-branches, and if our input is less than 0, then we're going to replace N70. We're going to overwrite that with 32, which is our low value from our scale. And if our input happens to be higher than the high level, which is 16383, then we're going to overwrite our N70 with our high scale value of 212. And what that means is by the time we get to rung 1, no ifs, ands, or buts about it, we're going to have a value coming into our process variable between 32 and 212 inclusive. So that means we've protected our PID from any abstract math. And that's it. Those are the ins and outs of PID control loops. Obviously there's some more complexity, especially when you get into different ways to set this up, how to run one in manual mode, using STI mode and putting an interrupt into the program to control it. But those are more advanced topics. This again is not that advanced course. However, the instruction in this lecture is going to get you through most of the instances that you will encounter using a PID control. You have just made it through section 7 of PLC programming from scratch, and by now you're developing a pretty technical understanding of PLC programming and controls. At this point, you really should be able to start visualizing processes. When you start approaching a program, you should really understand how a pump works, how a tank works, what we need to do to control temperature. These things should start becoming paramount in your mind whenever you're looking in a programming window and deciding what kind of logic to put down. You should be comfortable with the idea of HOA controls. They're very standard on digital devices. A lot of times you even have HOA controls on analog devices, so it's something necessary. It's something customers are going to want. It should be something that is in almost every one of your programs, maybe not for every device, but certainly for several. We've gone through a few different examples: tank level control programming, HOA programming. We've even done some PID control. You should have a good general understanding of those concepts, and if for any reason you don't, not to sound like a broken record, but please take 10 minutes or 5 minutes or 20 minutes out of your busy day. Go back through those lessons. If there's anything that you're only 60 or 80% sure about, go back through it. Don't be in a race to get through the whole course. It's going to be there for you. Take your time, get the most out of it. If you do, by the time this thing's over, you will be ready to start programming PLCs. Going into our next section, we're going to start talking about alarms and notifications. So it's going to be a lot more logic. It's going to be a lot more programming fundamentals. It's not going to be anything easy from here on out. So make sure you understand everything up to this point before proceeding. And when you do, I'll be waiting. See you then.